All right, good afternoon. How you guys doing? Doing all right? Okay. So today, I will get a little bit of feedback from you at the end of the class. So if you think a little bit about the syllabus, we'll take a look again. But just consider what we talked about last time in terms of which topics we're going to be covering. If you have some thoughts on what you're not comfortable with, what you are comfortable with, or maybe what you want to learn more about, I do have a little bit of flexibility to cater my class accordingly. So I'll get your feedback. You're also welcome to write anything else you wanna say. I don't need you to put your name on it. If you wanted to keep it anonymous, that's fine. There's a spot for your name, and maybe that's nice so that I can say, oh, okay, so and so wants more on this, and I could shoot you an email if I had some resources. So feel free, whichever way you like. Today we're going to work on some things that hopefully is review, at least at the start, for most of you. Any of you that have had any of my classes before have probably seen some of this in some shape or form. And then we'll go into some pieces that I think would be new to everybody, and at least touch on things, some more in-depth topics that we could go to for forming what we call mass balances. So a mass balance being the way we understand and model physical, chemical, any sort of reaction that we might be doing or observing in an environmental system, right? So the point being, we will today be going through some of the fundamentals, and the first really unit of our course is building, using, manipulating mass balances to understand environmental systems that we're designing or studying. Okay, so I'm going to start the basics here. Units are essential, right? I was teaching this exact same thing, at least this slide, basically, in my undergraduate course on water and wastewater treatment, because everybody needs a reminder, right? Pay attention to your units. If nothing else, take a look at your units and make sure things make sense. Make sure you're not trying to solve for time and giving me meters, right? You're shooting yourself in the foot, or that will help you realize, oh, hey, I did something wrong. I got the wrong constant, I put the constant in the wrong spot, something, right? So pay attention to your units. We always will be operating on the principle of conservation of mass. In some cases, maybe matter if we're don't necessarily have the information on mass, or maybe we will do a mass balance in the number of molecules, right? A chemical reaction we typically use in molar units, which is we can convert to mass, but it's conservation of matter is what we're really dealing with. Or likewise, maybe we disinfect some bacteria, and even though we're not weighing out the bacteria and getting some mass metric, or concerning ourselves with that, what we might be concerning ourselves with is how many active infectious organisms are there. So a matter balance in some sort. We're going to call it mass balance in general. Okay, in each case where we're doing some mass balance, what we're really interested in is how does some mass or matter change over time. So anytime we are setting up an equation, we will ultimately have mass per time. Now, a lot of times we'll be doing a concentration in the context of some volume. So many times we'll see something like a volume times the change in concentration per change in time, right? Putting these two together, we get mass per time. So anytime we're dealing with a mass balance, where it's really a mass rate of change that we're balancing. If we had a scale with a kilogram of water on one end and something else on the other end, we could do a mass balance that way, but if we're not concerned about what's happening over time, it's not very interesting, right? That when we apply the time term, then we have some activity and everything becomes a little more interesting and useful. Interesting to us and useful for us. Okay, so focusing on the units then, and attending to the fact that we're all boiling down to mass per time in some shape or form. That can help you solve a lot of problems, even if you forget or get stuck or something. Just remind yourself, come back to the units, double check. Make sure you're familiar with common unit conversions, of course, the SI units. I'm just as a blanket going to expect you all to be very familiar, capable, get help if you need any help. But if I ask you what's a milligram or how many micrograms are there in a nanogram, you should be able to tell me, right? And that one was backwards, right? There's a very small number of micrograms in a nanogram. So if any of that doesn't make sense, or if you're, don't be afraid to speak up and ask, but make sure you're familiar with SI conversions, all that stuff. Okay, for mass balances, have our little balance here as kind of the visual example. What we're really going to talk about is the rate at which some species, maybe it's a chemical, maybe it's a bacteria, maybe it's a gas, whatever it is, how its concentration changes by entering or exiting or going through some sort of a reaction within a defined space. Okay, so we're going to define a space we will call a control volume. Let's make it better. So we'll have some control volume. And what we're going to do with a mass balance is aim to study exactly what's happening as any of I is crossing in or out, or undergoing some sort of transformation inside, whether that's growth, decay, or whatever. So our mass balance then, when we define some area, we can consider it as measuring the accumulation within that area. And the ways it can accumulate are stuff entering, stuff leaving, growing, or decaying. Okay, those are all of our possible terms to understand that, to define that mass balance. So we could write that as the total accumulation rate would be equal to any input rates or a net input rate. We could have more than one input, right? We could have many inputs, potentially, minus any output rates or a net output rate. This would be anything leaving that boundary. Again, we could have multiple exits. There's nothing wrong with that. And then we'd have plus anything that's going to add in a positive way to accumulation are the inputs and the growth reactions, right? So we could say growth rate or growth reaction minus a decay reaction. Now, if we, using all of these terms, put each one of them into a mass per time net unit, then we can deal with an accumulation rate that is in mass per time, and everything should be happy. So at the bottom here, we see a typical look at this. If we have, we'll just summarize it into one flow in times the concentration that's coming in, minus one flow out times the concentration going out. Of course, we could have multiples of each of these. Well, let's just stick with one for each category for the moment. Then it would look something like this. Q, a flow rate, so Q being a flow coming in, times the concentration of some species I coming in, minus Q, and actually one thing I'll do here is that'll be, Q will be a volume per time, concentration will be a mass per volume, or number, something, some quantity of the substance per time, or excuse me, per volume for the concentration. We'll have the same units here, and actually, yeah, so we'll just write that out. V over T times M over V. Then our reaction term, we have some rate of change times the volume. And that rate of change, R, if we stop and think about it, we could think about it two ways. One would be, what is a rate of change going to look like? It's going to be some rate at which some substance is changing over time. And usually we're quantifying that, if we're going to measure it, with a concentration. So that how the concentration changes, a reaction would change a concentration over time. And so the other way to think about that is how to get this into mass per time units. Well, if we have a volume, then we need mass per time also divided by a volume. So that gives us concentration per time. Okay, so this R should be, I'm just going to, I've repeated this, so I'm just going to get rid of that for the moment. R would be that mass per time also per volume, because then we're going to multiply that volume for the volume term there. So these will cancel. We'll see that's mass per time. Okay, it doesn't really matter how we're dealing with this. We could even say, I am scooping 1 kilogram of calcium chloride into the reactor every minute. That's a mass per time addition. Okay, it's already in mass per time units, so I don't need a volume. I don't need a flow rate. I don't need any of that. It's a mass per time addition. So you'll see sometimes problems will have a diagram like that, and then they'll say there's an input. And you'll notice the units are mass per time input. It's still an input. It would act a lot like one of these input flow rates. It just doesn't have any flow because it's, I don't know, some mass over time, right? Oops. Sorry. That could all work just the same as a flow rate, except we're not adding any water. So what I'm trying to paint here is the picture that it doesn't really matter exactly how we're putting inputs. It's just whenever something's crossing our control boundary, that's when we have an input. Okay, so we've got inputs, outputs, growth reactions, decay reactions. Next time we'll get into a little more about the reactions, at least I think that's next time, to define, okay, what is a first order, zero order, second order? What does that mean? What kind of reaction vessels are important for that? Things of that nature. But this is the big picture of a mass balance, is we're going to define some area that we're interested in and set up, okay, how are things changing across that? Does that make sense? Most of you seen this before, but some of you maybe it's kind of a little bit new. Is that about right? Mostly just ready to be done for the day? No reactions? All right, I'll make you talk in a few minutes maybe. All right, so if we follow our book, we can take formalized steps to define our control volumes and elaborate a given problem. Real quick, here's a picture of a typical schematic that we might use for a few different types of water treatment systems. One could be a wastewater plant where we have some biological treatment here, followed by a clarifier, and then we want to separate all the bacteria that we're growing and let them accumulate into some sludge, sedimentation chamber, or clarifier, whatever you want to call it. Then we have some cleaner water leaving, some dirty water coming here to go to the waste, and then maybe recycling some. It turns out this is also a way we can do some coagulation and sedimentation. If we have some, and I think we have an example from the book in a moment, we could have some precipitation occurring in here to remove some dissolved solids and then letting those solids settle. And sometimes we might even recycle some of those in order to act as seeds for other precipitates to have an easier time beginning the precipitation process. So it turns out this is a pretty common schematic in water treatment where we have a sedimentation chamber. This allows us to separate solids from the liquids just using gravity. We're going to take a deeper dive into that later. But the point is, we can define a few different control volumes with this system depending on what we decide is the appropriate spot to draw our boundary. Right, so we could draw the boundary with a dashed line here in A. We could take a look just at that clarifier system here, B, or we could draw it around the entire system with C. And what you'll notice is whatever solution or problem that we're working on is going to look a lot different. We're going to need different information or have different information based on where we're drawing this. Right? The inputs and the outputs are different. You know, maybe there's something different happening in here in the clarifier. We'll take a look at an example that says, assume no reactions happening here. That's a pretty common assumption, so that we have our reactor doing the reaction and this is just doing the sedimentation. Makes the math and assumptions a little bit just cleaner. And so depending on where we draw that, that's going to define the entrances, exits, and potentially the reaction. So that's the instructions we have here. Define what it is we're looking for. Maybe in this case, maybe in some case, in a wastewater case, maybe we're looking at BOD, biological oxygen demand, and our microbes are consuming it. I think in the example we're going to look at, it'll be a softening type system, so we're precipitating calcium carbonate. So what's the calcium concentration? What is this I? So we're going to define that, draw the CV, the control volume, based on what we need. If we notice, we need to figure out what the Q, the final Q here is. Well, we don't really want to define it with A because that doesn't give us the information very directly. Maybe we want to do B or C. Then we might ask ourselves, well, do we have enough information where B is the most useful, or should we just go with C? Turns out C is often a pretty convenient way to do it because you cut out a lot of that middle stuff that's just recycling. And you just look at the net in and the two net outs. Okay, so essentially that's 1 and 2, and we just talked about 3. Of course, then we need to define any reactions that we might have within our vessel, our chamber. All right, so let's take a step back to a very easy problem and give you a chance to see what it feels like to do this on your own. All right, so this is an example I use in my other class. So this is a very beginner type of problem. I'll read it with you, give you a chance to take a look at it and walk you through it. So we have a stream flowing at 10 cubic meters per second. It's got a tributary feeding into it with a flow of 5 cubic meters per second. The stream's concentration of chloride upstream of the junction is 20 milligrams per liter, and the tributary chloride concentration is 40 milligrams per liter. Treating chloride as a conservative substance, that means we have no reactions happening. And assuming complete mixing of the two streams, find the downstream chloride concentration. Okay, so go ahead and see if you can solve this in 3 or 4 minutes. All right, looks like you've all had a chance to get going on it and at least face the point where you're trying to solve, maybe get stuck. And I realize one thing that I didn't even mention yet, one of the foundational things, is for many cases, we're going to make an assumption. And we'll talk more about it. But in many cases, if we let a system run for some time, we'll reach a steady state, is what we say, where we are no longer accumulating upwards or downwards I in our control volume. Now, that is a special condition called steady state, and we typically try to design for that. In the case of two streams coming together, if their flows and concentrations are constant, we'll reach it very quickly. Because there's no reactions happening in there, there's nothing interesting. As long as those two concentrations stay the same, then the amount of chloride that just happens to be in that volume, whatever that volume is, it's going to remain pretty constant. And that's what I mean by accumulation. We're not getting more and more chloride in here because as much as is coming in is leaving. So in this case, it's so simple of a problem that maybe that was intuitive already. The inputs are going to be equal to the outputs. But to mathematically get there, we need to assume we are at steady state, which is putting the accumulation rate to 0. So I think as we talk about reactions and reactors, we'll make a bigger point of that and talk about cases when it's not. But if we assume steady state, that means the accumulation goes to 0. Does that make sense? If you haven't seen that before. All right, so then we can more easily say 0 equals in minus out. There were no reactions because we said it's conservative. So that means input equals output. The two inputs here would be QSCS plus WCW, going to be equal to the CMQM. And again, each of these, when we take a concentration times the flow rate, we're going to get a mass per time. So in each case, we're getting mass per time units. Even though we put accumulation to 0, we should still treat it as mass per time, right? So the units still need to come up to mass per time. Now, if we put in these numbers, we have 20 times 10 and then 5 times 40. Turns out both of those come to 200 each, so that becomes 400 milligrams per liter times cubic meters per second on the left-hand side. On the right-hand side, we're not given QM or CM, and what we're trying to solve for is CM. Hopefully, you can see that the QM, we're not given any information about random other sources of water entering the system, so the flow rate should be the sum of the two, right? So the Q in this case, Q mixture, should be the 10 plus 5 cubic meters per second. That's 15, right? Okay, so then we have this QM there, and all we need to do is solve for the CM. And I'll just go ahead and put this over on the other side and say this is 400 divided by... What? I took a shortcut, and I'll elaborate. I was just a little short on space. I did mean to write 400, but it's not. If you're asking that, it's not very clear. So let me write it out a little more explicitly. So what I ought to write is each value for the Q, the C, so QS, CS, QW, CW. So, but what I was referring to is QS is 20.0 milligrams per liter. Multiply that by our 10 cubic meters per second plus the 40.0 milligrams per liter times 5 cubic meters per second. Those are the inputs, and if you do that, you will end up with 400 because 20 times 10 is 200. 40 times 5 is also 200. Add them together. I just took a shortcut to add them all together to say 400 milligrams per liter times cubic meters per second. So that's on the left side of the equation. Those are the inputs. So on the right side of the equation, we have QM, CM. We're trying to solve for CM. I'm going to go ahead and divide both sides by QM, which was 15.0 cubic meters per second. So that should give us, if anybody's got that, I think it's 26.67. Okay. Milligrams per liter. Good thing to do, we could take a look and check to make sure that appears valid. So we have two concentrations given in these two streams coming together. One is 20 milligrams per liter and the other is 40 milligrams per liter. They're different flow rates, but the flow rates are kind of similar, so I'd kind of expect the value, the ending value, to be somewhere between them. I don't see how it could be larger than either of them or smaller than either of them, right? So 26 is between the two. At least that checks out, right? So we didn't do anything crazy wrong. I'm confident that is our correct answer. Okay, once I said the steady state assumption, did this problem make sense? Okay, you're good on it at that point? Any questions or issues? Okay. I know if you haven't seen mass balances much, you'll see plenty, but I want to just take a slightly slower start here. Because when we get to the book, our book, it's going to have us jump in a little more, with a little more depth here. Can you read this in the back? Is this big enough? Okay. All right. So here's another example. And I'm going to skip forward a little bit just to show you what we're asked to do, but then I'll go back and read it with you. It's asking us to write mass balances using appropriate control volumes in order to solve for the concentrations of I in three different pipes, okay? And that happens to be pipe 3, 6, and 7. So this guy, and this guy. All right, so as we take a look, just keep that in mind. Our challenge is to, kind of like the last problem, do some sort of mass balances in order to figure out what's going on in this system. Right, so in this particular example, it says a common approach to soften water is to adjust the chemistry of the solution to cause calcium carbonate, CaCO3, solids to precipitate. We can often use a flow diagram like this. It's what I was pulling the figure from earlier. New solids are generated in the main reaction tank. So we have a reaction to produce solids here. That's meaning that calcium will be removed from solution. So depending on what we're solving for, our Ca2 plus would be removed as a decay reaction, or our solids would be produced as a growth reaction, okay? I think we're going to solve for calcium concentration, so we're probably looking at a decay reaction, but this is just, I'm saying this and elaborating just kind of so you have that in mind. We could go either way with this. Maybe we're trying to figure out how much solids are we producing per day so that we can order enough dump trucks to take it to the landfill or whatever, right? You know, that's the type of thing we could look at here. Okay, so rather than discarding all the solids, a fraction of the settled sludge will be returned. That provides seed crystals. I actually already explained that for the new precipitates. Okay, the advantage will be discussed in chapter 9 in case you're curious. I don't think we're covering that directly, so we just get a little sneak peek here. So the chemical reaction is Ca plus CO3 2 minus gives us CaCO3 solids. Okay, a proposed water softening process will treat a flow of 3 cubic meters per second. The objective is to induce precipitation of these solids to reduce dissolved calcium to a concentration from 150 milligrams per liter to 40. The influent contains no calcium carbonate solids. The settling step is expected to be very efficient, so we're settling all of the solids, essentially. It's a nice assumption for us. And that means we can assume that the CaCO3 solid concentration of the treated effluent for the system, that means whatever's making it out of the clarifier here, that should be 0 for the solids. Okay, so that's also convenient. Okay. So it shows this particular figure. It's a little more specific, and we see these specific pipes and the different control volumes we could draw. So with these 3 control volumes drawn up here already, we have to decide which ones to use to answer the 3 pipe questions, right? So that's kind of where we're heading here. All right, the flow rates are indicated at the points indicated are as follows. It gives us 7 flow rates here. And then it says, assuming the water volumes in the various tanks, assuming that the water volumes in the various tanks, the water flow rates and the concentrations of all the chemicals in the system are steady over time. So that just gave us the steady state condition, right, in each scenario. Write mass balances using appropriate control volumes to determine the concentrations of calcium carbonate solids in the pipe between the main reactor and the settling basin. So that's pipe 3. So that does pertain to solids. Then the pipe leading to the sludge processing facility, that's this guy here, pipe 6, and the pipe conveying recycled solids to the main reaction vessel, pipe 7. Okay, so I was wrong. Maybe we'll talk about the calcium later, but or perhaps we might need to relate it back to our conditions at the start. So maybe we will use it. But essentially, as we form solids of the calcium carbonate, we are removing the dissolved. And we were given information about how it's designed in terms of how much calcium to remove. So in fact, maybe we're going to go start from there and decide how much solids are being generated based on that removal of calcium. I think that's probably actually what the problem's asking us to do. Okay, it also says assume that no precipitation, that precipitation occurs only in the reactor and not the settling tank. So that means when we talk about this reaction here, we can just deal with this particular volume and not worry about that reaction maybe happening in the other tank. That's just going to simplify our control volume and reaction calculations. Okay, there's a lot here. It's a lot of pieces. So what I'm going to have you do, oops, I meant to delete that. I think this might be, I perhaps did not get the updated version, or it just didn't save on my desktop. Anyway, I have those solutions so that we're not lost, but I didn't want you to have them just yet. I wanted you to try it. So I encourage you to work together on this, but remember we have these 2 assumptions. It's well mixed, we're at steady state, and what we're trying to find, it was 3, 6, and 7, and that's the solids concentrations, CaCO3 solids. We want a mass balance to determine the concentration of CaCO3 solids in milligrams per liter. Oops. And each of these locations, given this situation. The other thing we probably need to know, I think this part is given, but we need to reduce the calcium concentration, Ca2 plus, from 150 to 40 milligrams per liter. So we can say, in the input, Ca is 150 milligrams per liter, and the output here is 40, so Ca is 40 milligrams per liter there. I'm just gonna okay, so I think you have the information there. I'll say go ahead and get together if you'd like. See how far you can get. I'm going to give you a little bit of time, and I'll probably sketch up some pieces of it that seem to make sense to me as a starting point as we go. I'll do that silently so you can keep focused on what you want to do, or you can kind of glance up to see if you need a starting point help there. But like I said, feel free to work together. Yeah. And let me know, what information do you need from it? Is it, like, what are you looking for? Is it the reaction here?
No, the overall.
Just the overall? Okay. I'll move it forward in a few minutes as I start some of the solution.
Are you assuming that they don't add any excess carbonate?
I think we can assume that the carbonate, there's going to be carbonate probably from the atmosphere, honestly. So there's probably a perpetual supply of it, and it will be sufficient to achieve, given this reaction, to achieve this reduction. I think that's probably the best way to look at it. So it's rather than carbonate being a factor, it's really the calcium that's the factor that we need to look at. Concentration of what? Yeah. So a good point in question there. With a clarifier like this, we have liquid water with dissolved stuff flowing in two directions, right? From 3, we enter the clarifier. We have liquid going out here and some liquid going out here. Anything that's dissolved is not going to be separated by gravity, right? So the concentration of anything dissolved should be the same in those two outputs. Now, the difference here is we're changing the concentration of settlable stuff. So the concentration of the solids, we said, would be 0 in this part, and all of it goes out this part. So as we consider the concentrations, whatever calcium concentration is here should be the same as is here, and even in 7. Sorry. right, I'm going to give you a kind of a launching point, maybe a check-in here. So when I take a look at the problem, a couple things stand out. If we're trying to find 3, 6, and 7, based on the similar thing we said earlier, where we have a flow split into two ways, if there's nothing doing any sort of separation, the concentration in those two flows are going to be the same, right? So when we split from 5 to 6 and 7, the concentrations here should be the same. So when we're trying to solve for 6 and 7, if we solve for 1, we know the other. Now the flow rates might change, but I think those are given, so we can handle that. So that seemed like, to me, an easy place to start would be the widest control volume, where we have 1 input and 2 outputs. Okay, so I thought to myself, well, let me see how far I can get with the solution for the concentration of solids. I'm writing this as CS, comma 6, which would equal CS 7. And so I took control volume B that's spanning the whole thing. Okay, when I set up a mass balance there, took it at steady state, so 0 is the net accumulation. We had our inputs and 2 outputs. But if you think about it, we were told explicitly that we are growing solids, so we need a reaction term within the reaction vessel. It also wouldn't make any sense to have 0 coming in, 0 going out here, and suddenly we have some going out here. We have to have a reaction to balance that. But given these two zeros, we notice that the CS coming in, that term should go to 0, and the CS going out the clarifier should also go to 0. So it does simplify very nicely our setup to understand something about the reaction term. That would mean that the amount that we are wasting out this discharge pipe is exactly the same mass rate of change as we are growing in this reaction chamber, given this control volume. That's quite convenient, but we still need to know something about this RG value. And I don't remember if we're given anything about the volume of this tank either. I don't think we need the volume, but just double check. Yeah, I think we can solve it fine without, because, oops, I just hit end again. We did not do that. We actually don't need it in this volume times the rate, because what we're looking for here is a mass per time, and we should be able to get that based on the fact that our calcium initially goes from 150 milligrams per liter to 40 milligrams per liter. So I'm going to give you a few minutes to consider how to convert this change that we were told into a term that can go here. All right, so that would be the next step in my books. All right, take another 5 or 10 minutes, see if you can get the problem from here. How far did you get? Stuck? Some sort of answer? All the way?
How would you iterate to the third thousand?
So you got an answer for it? Okay, good. Yeah, and I can double check, and I think that and we also need an answer for the other portion too. But so I'm going to finish the solution with you. I'm just kind of trying to gauge how far did you feel like you were able to get an answer? Not quite. Still lost. Where are you at? Got an answer, just not sure about it. Okay. Anything like on your mind, like how do I do this? Brave enough to ask? Yeah.
Does it make sense to like get a series of equations and then figure out if we could plug some into others and then figure out like what you know versus what you don't know?
I think that can work sometimes, and maybe that's essentially what we do, even if we take it one by one. And so there's probably a way to take the solution I'm about to give you and instead write it out as a series and kind of solve them simultaneously, I would guess. So I could certainly see that as a possibility. It's not the way I typically approach it, but I'm not saying it can't be done that way. Okay, so as you see from here, what I started to do to kind of guide us along figuring out what is this growth rate for the calcium carbonate in solution as solids, we need a mass balance on calcium ions. Like I mentioned, we go from 150 milligrams per liter to 40. I went ahead and brought in the molecular weights. So calcium, the atomic weight for calcium is approximately 40 grams per mole. And for calcium carbonate, it's very conveniently 100 grams per mole. So if we stop and think about doing a mass balance on calcium ions and then converting that to a mass of calcium carbonate, we'll need to do a molar conversion, right? So that's kind of where I paused here, in fact. So we've got an accumulation rate. Again, if we draw the big control volume looking at mass balance on calcium, we've got the 150 coming in. Maybe what I'll do, if I can ever find my cursor here, I'll just highlight the 150 coming in here, and then we have 40 leaving here and also here. So we could kind of sum up those two flow rates into one as the output terms, and that would work just fine. Okay, so continuing the solution then, we have, again, steady state. 0 is our accumulation rate, equals 150 milligrams per liter coming in times that flow rate coming in, minus 40 milligrams per liter with the flow rate at 4, minus 40 milligrams per liter at the flow rate at number 6. And all of that minus the decay rate of calcium ions, right? So we have to add in that term. But now we have a bunch of known values and the one unknown. So we can say, okay, the decay rate is this. So previously we had the unknown rate here for the rate of growth and an unknown for the concentration at that value. So we can relate the growth rate to the decay rate as long as we do the molar conversion. So that's what I'm doing here. We are solving for the decay rate, and in fact, I went ahead and got the number. If I just added VRD to both sides, then what was remaining on the right is this 330,000 milligrams calcium per second. So here, I'm going to go ahead and convert that. We're going to go ahead and put that into molar units times 1 mole Ca2 plus per 40 grams Ca2 plus. Then we can convert that over to, by multiplying by 100 grams of CaCO3 solids per 1 mole. So essentially what we'll do is we'll cancel the moles and we'll be left with milligrams of CaCO3 instead of the milligrams of Ca2+. So just doing the molar conversion there. And this should give us a value of 825,000 milligrams of CaCO3 solids per second. As a growth rate, because I just converted this, decay rate of calcium should be equivalent to the growth rate of the calcium carbonate. Assuming we do that molar conversion, then it should be our growth rate. It is a 1-to-1 molar situation, as is kind of obvious and was shown here, right? So we have 1 mole calcium for 1 mole calcium carbonate. Okay, so all that together, that should then give us a value for the VRG for calcium carbonate. Okay, from there, we can take this, probably need to double check that our units are good and everything, and plop it in there. Does that make sense? Okay, so we found that by finding the decay rate of the calcium itself. All right. When we do that and we solve for, that would also go right here. We could then solve for that, and we'll go ahead and do so here. So we say the concentration of solids at pipe 6 should be essentially dividing that 825,000 number by that flow rate. And what I have written here would be that's 9,821 milligrams per liter, which should also be the concentration of solids in pipe 7. Does that check out? Okay, and just doing a rough check on the top of my head, we had just over 800,000, and we're dividing this by a number 84. That's almost 100, so we're taking 825,000 divided by almost 100 should bring us down to the 8,000 to 9,000 range, right? So that actually feels like it's the correct answer, even though I didn't do it today. This is last time's notes. Okay, but kind of makes some sense how we got there. All right, then the last part here would be to find the concentration of solids at pipe number 3. Okay, so with that, we can do one more mass balance, and this time we need a different control volume. Maybe you could do one on, might be able to use that one, or you might be able to use that one. So I went ahead and used control volume A for this to say 0 is going to be what's coming in, Q1 times CS1, which is 0, plus what's coming in from Q7. Got to remember that one. Q7 times CS7, now that we have that information, minus what's going out, which is that 3. CS3 times Q3. We should also have the growth term in there, which I did not include last time I solved this. But I don't see why we wouldn't. So I have a tiny bit of homework to correct this, I think. Right there. Okay, I'm going to double check on that part before next time. So I'm going to pass out these for some feedback. I think what I'll do, I've only gotten through 7 slides. I was thinking to myself, well, I've only got 11 or 12 slides here. Is that doesn't seem like enough. So we have a few more things to talk about in terms of what else impacts mass balances. So what I will do is I'll pass these out. I'll pull up the syllabus so you can take a look at the current course plan, so you can kind of see the materials. Any questions? We will resume with that problem and wrap it up, but any questions about it or anything else? Okay. Is that too small? So everything before exam 1 is reactor, flow, kinetics, reactors, reactions, and then that stuff. What's that? Yeah, you could bring it back next time. That's fine.